Hey, what's up, chem peeps? Now it's time for some pH calculations of weak acids and weak bases. A 0.100 molar weak acid solution has a pH of 4.25. Find the Ka for the acid. Okay, I know that my weak acid, when placed in water, is going to have a general equation that looks like what you see on your screen. And based on that equation, my Ka expression, boom! So how do I figure out the value of Ka? Well, I know one part of this. I know the concentration of the weak acid is 0.100 molar. But how do I determine the concentration of the hydronium ion and the concentration of the conjugate base A-? Well, the only other thing I'm given in the problem is the pH of the weak acid solution to be 4.25. And I know from my formula chart that pH is equal to the negative log of the hydronium ion concentration, which is what I need. So if pH is 4.25, all I have to do is solve for x and I've got my hydronium ion concentration. Remember, first I'm going to divide each side by -1 for -4.25 is equal to log of x. Then we're going to go exponential on this thing. It's going to be 10 to the negative 4.25 equals x. Jump to my calculator. Second, log -4.25, answer. X equals 5.6 times 10 to the -5 molar. Again, that's my hydronium ion concentration. So I'm just going to take that and plug it up here into my Ka expression and recognize that it's also going to be the concentration of my conjugate base A-. So a quick jump to the calculator, we're just going to square our concentration of hydronium ion, enter, and then divide that by 0.1, enter, to get the value of Ka to be 3.2 times 10 to the -8. Boom. Now, if you're wondering to yourself, what the heck is going on? Think about this in terms of an ice table. We knew the original concentration of this acid was 0.100 molar. Initial concentrations of these things were both 0. We're told the pH, so essentially we know what the equilibrium concentration of hydronium ion is. It's 5.6 times 10 to the -5. And because stoichiometrically those things have a 1-to-1 ratio, the equilibrium concentration of this is also 5.6 times 10 to the -5. The changes here, they each increased by 5.6 times 10 to the -5, which means that the concentration of our acid must have decreased by 5.6 times 10 to the -5. But if I jump to my calculator, they're far enough apart that it isn't going to make a substantial decrease. Second E, -5, close parentheses, enter. Notice that if I round to the thousands place, this is still going to round to 0.100 molar. Ice tables, always bringing clarity to these problems. And we are done.